We've been working with the Cartesian coordinate system so far for the entire course. We're very familiar with the Cartesian coordinate system. Now we're going to introduce another coordinate system that overlays on top of the Cartesian coordinate system called the polar system. So the Cartesian coordinate system that we're used to working with has the x and the y-axis. And with the x and the y-axis we can easily find angles like 45 degrees or 30 degrees, and of course the 90 degree would be the vertical. But what the polar graphing system or graphing polar points is instead of using an xy as an ordered pair, it uses r and theta, where r stands for radius and theta stands for the angle that's created with the initial side on the x-axis and the terminal side, wherever we're going toward. And it is affected by the radius, whether the radius is positive or negative. So there's a little bit more to it than just saying r and then going out that far onto the axis, because it matters whether it's a negative r or not. Now the difference with the polar equations then that we're going to be looking at is we have a circle with different radius. So this would be a circle with radius 2. This would be a circle with radius 3. And you probably kind of get the idea here. Here would be a circle with radius 4. So this is kind of what we would look at. And again, it overlays nicely on the xy axis. So we need to be able to convert between polar points, r theta, and rectangular points, xy. So let me go ahead and copy this before I write on it so I can reuse it. And let's go ahead and plot some points. So again, like I said, the relationship here is r theta is a polar point, and xy is a rectangular point, and they are connected. And so let's go ahead and look in that first quadrant, and we can see the relationship between those 2 points. So here's my angle theta, here's r, so this would be the point right here, r theta. However, that has some sort of a connection to these points as well of xy. So this is also the point xy. So we need to be able to make the connection between these points. So let's go ahead and start by plotting some points. Let's go ahead and plot the point P to 30 degrees. Now, usually we have the degree mark in here. I was looking through the homework just to kind of see what was the consistent way that they noted these. And sometimes they don't put in the degrees, it seems like, but they usually do. So whenever you see a point that looks like it's an angle of some sort, and of course we absolutely could use radians here, it probably is an angle. If there's no degree, you can be sure it's rectangular, but again, always kind of read the directions and double check with that. So again, this is r theta. Now because of the circular nature of the polar coordinate system and the fact that we can spin around the unit circle multiple times, there's more than one way to describe a point. Rectangular, let's say I had the point 2, 7. There's only way to describe that point 2, 7, and that's with the ordered pair x is 2, y is 7. Polar points are not unique, and we're going to go ahead and show how that works. So for here, it says 2, my radius of 2, so that means I'm going to be somewhere on this circle because I'm 2 units out. And then it says I have to be 30 degrees out. So 30 degrees would be right here. So it would be this point on the circle. So that's the point that I'm talking about right here. So that is the point to 30 degrees. So it's not this entire line, it's just this point P right here. Now there's other ways I could describe this. So another way I could describe P is 2 units out, but I could look at this in terms of, let's say, spinning the full 360 around the unit circle and then another 30, which would be 390 degrees. So that also describes this point. I could go in the negative direction. So if I went negative 90, negative 180, negative 270, this would come clear around and I would end up at negative 330 degrees. So that would describe this point as well. And again, I could spin multiple times in the positive or negative direction and almost have like an infinite number of ways to describe this point. Now, one thing that we haven't talked about is, what about a negative radius? Okay, so what would that look like? Well, the effect of a negative radius means to reflect. So what I would do if I had this -2, that would put me at this point right here. Okay, so what we want to think about is what is this angle measure right here that would allow me to plot it, and then the negative part would say to reflect it right back to here. So this would be, and again this has to be 30 degrees is my reference angle here, so that means this is 30 degrees. This would be 180 plus 30, which is 210 degrees. So to plot this point, I would do the -2. So I'd move in that negative direction. I guess not negative direction. Let's do it this way. Let's do 210. So let's plot 210 on a radius of 2. And then we'll reflect it back to this point with the negative. So let's do another one of those. I want a -2. And for this one, let's go -120. So if I were to plot this point, so here I'm starting, I'm moving in the negative direction, -90. -120 puts me right here, but then because the 2 is negative, I reflect it back to this point. So that keeps describing the same point. So we're seeing the same point over and over again. We're going to practice this a few more times because getting used to that negative radius can be a little bit confusing. Okay, so again we have our polar coordinate system out. Let's go ahead and look at the point Q. And this point Q would be -4, 2 pi over 3. So I think what I would like to do is plot the 2 pi over 3 first. And again, 2 pi over 3 would be 120 degrees. So it would be this line or this angle right here. So here is 2 pi over 3 or 120 degrees. Now this says to move 4 out onto the radius, 1, 2, 3, 4. So that would be my next point. And then this negative means to reflect it. So it plots me to this point right here. Okay, so a couple things to keep in mind. This whole angle is 2 pi over 3. Excuse me. This is pi over 6 here. So that means this would have to be pi over 6 here. It's a vertical angle. Oops, pi over 6. So if I wanted to describe this point several different ways, I think one of those ways that we could do that is to keep that -4 to end up here. This would be a -4 pi over 3 would describe that point as well. So I go -4 pi over 3, hit that point, and negate it into quadrant 4. Let's go ahead and look at 4. And then if I look at this radius moving in this direction, or this angle in this direction, that would be a -pi over 3. I could also think about spinning more than one time around the unit circle. So this would be 6 pi over 3, 7 pi over 3, 8 pi over 3, -4. So again, I could write an infinite number of these. Usually in your instructions they ask you to do something within, let's say, 0 to 360 or something similar to that. They'll give you some instructions along those lines. Let's do one more. For this one we're going to call this point R. And this point R would be 2, or sorry, let's do 5. We can't do 5. I don't have enough circles. Let's do 3, -pi over 4. So let's go ahead and do the -pi over 4 first. Bisects the fourth quadrant. So this is the angle -pi over 4, and then this says to go out 3 in terms of the radius. So it's this point right here. So this is the point R. Well, how else could we describe this point? Well, we have an infinite number of ways we could describe it. I could move in the positive direction to end up in this same point, and this would be 4 pi over 4, 5 pi over 4, 6 pi over 4 would be 7 pi over 4. That would be another way to describe it, except I know my radius is 3. Let's go ahead and look at one where we have a -3 here. So basically what would happen is I would have to plot this point and then make it negative to reflect back. Well, that is the point 3 pi over 4. So if I do 3 pi over 4, go out 3 units and then negate it or reflect it into the fourth quadrant, it works perfect. So that's the polar coordinate system. We're going to be working with it quite a bit. We also have a few other notes that we need to make and keep in mind, and these are for your note card. We've already written these down before, but I want you to remember about a couple of these values that we use over and over again. So x equal r cosine theta, because cosine theta equals x over r. Same type of thing for y equal r sine theta, And then remember that tangent theta is y over x. And of course, x cannot equal 0 or the fraction would be undefined. Also keep in mind we use r squared equals x squared plus y squared. And if we solve that for r, I get the square root of x squared plus y squared. So we've used these before, but I just want you to be aware we're using them again. So either create a new note card for this section or keep in mind or look back to those other note cards from previous sections. Okay, let's have a look at some problems. Now we can do more besides just plotting points in the polar coordinate system. We can actually draw equations or sketch equations. So let's go ahead and start getting used to working between the rectangular system and the polar system. So for here, what I want to do is I want to take this rectangular form, and the rectangular form will be x minus y equal 9, and I want to convert it to polar. Okay, now a couple things to keep in mind. I'm also going to be choosing graphs here. What I like to do with these types of problems is I like to graph them with the rectangular because I've worked with rectangular for so long and we're so familiar with rectangular that when possible and easy I'd like to convert them and keep them in rectangular form when I graph them. So for this one, please keep in mind if I solve for y here, I would get y equal to add the y across, subtract the 9, get y equal x minus 9. Well, this is a line with a y-intercept at -9 and with a slope of 1 over 1. So that's pretty easy to graph. So what this would look like, and again we're trying to overlay the polar coordinate system onto the rectangular coordinate system so we can see the similarities. So we have to have a y-intercept of -9, so I'm going to bring in this graph that will have at least 9 that we can work with. It's kind of a big one. Now this one, it's kind of hard to see where our x and our y axis would be, so I'm going to go ahead and copy over that piece. This would be the x-axis. This would be the y-axis. Okay, now instead of splitting this up into just maybe 45 degrees, they put a lot of different angles in here, and each of these is worth 15 degrees. So 15, 30, 45, 60, 75, and that would occur all the way around. So for this graph, what we're looking at is a y-intercept of -9. So let's go ahead and see if we can find that y-intercept of -9. It goes 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the slope of 1 is a little bit hard to see here. What ends up happening is each one of these radius that goes out, I could make a tick mark, and that would relate this to the rectangular coordinate system that we're used to as well. And the same for horizontal and vertical. So you can see there is a Cartesian coordinate system here. So from here, I would go up 1 and then over 1. And so I'm kind of looking at a graph like this. So this is the graph of y equal, and what did we decide that was? X minus 9. So y equal x minus 9. Okay, so that makes sense to me. However, now we need to convert to polar. So to convert to polar, what we're going to use is we're going to use equations that we used right up here up above to replace x with r cosine theta, y equal r sine theta, and then we're going to solve for r. So when we convert to polar, we want r equals stuff. Okay, so to start with, we had x, which is r cosine theta, minus y, which is r sine theta, equals 9. If I factor out an r, I'm left with cosine theta minus sine theta equals 9, and then divide both sides through by cosine theta minus sine theta. Cosine theta minus sine theta. These cancel. In the polar form of this graph then is 9 over cosine theta minus sine theta. Okay, now we haven't talked much about calculators and how they'll play into all of this. Now we did quite a few changes with the calculators in some of our previous lectures, so let's go ahead and make sure that we're kind of back to where we were starting with not everything in the complex system. So see where I have a plus bi here? I'm going to come up to mode. I'm in degree mode, that's fine. And then let's come down here, and instead of a plus bi, let's go ahead and put it in the real mode. Now we're going to be graphing as well. Now right now you'll see we have a y equal here. So if we wanted to graph this y equal, we could just go ahead and put in x minus 9 right now. Again, we might have to update our window here a little bit. We probably should go down to y min to be like maybe negative 15, because we know it goes down to negative 9. And then for our x max, we could go out maybe 10 or 15, it doesn't matter. So let's go ahead and hit graph. So there's that line. It's similar to the line that you see over here that we just graphed. Now, what about graphing this right here? I would not look at this graph and come up with the one that we have down here. So our calculators can help, but we have to get it in the right mode for that. So the mode that we want to go into is we hit mode, and we want to be in polar mode. We want to graph not in rectangular mode, but in polar mode. So let's go ahead and scroll down. If you notice, we're in function right now, the flashing one. Let's come over here to polar. Okay, now if we go to graph and y equal, you'll see instead of a y equal, we have r. So let's go ahead and put in this value for r. I'm going to use my fraction, alpha y equal, r equal 9 over cosine theta. Now when I click this button, instead of getting an x, I get a theta minus sine theta. And I hit graph, and there's that same line again. It looks a little different. We have to adjust our window maybe. I'm going to go to zoom trig here and see what happens. Well, that's even more or less interesting. Let's see if we can get it to some right settings. So I went and found that zoom standard worked really nice here. So zoom standard was option 6, and I got this nice graph. And we can see that it matches with what we have here. Okay, so using your calculator to look at these polar graphs is going to be really helpful. I can look at them in their standard form, rectangular form sometimes, depending on the graph, and also I can look at them in their polar form. So graphing to check your work will be really nice here. And it'll also be nice because in some of these problems, you're going to be graphing figures and shapes that we've never looked at before. So let's go ahead and look at some more problems where we're learning how to convert and how to graph. So for this next problem, we're going to be doing quite a few different things. First of all, we'll be looking at a polar point, r theta. Theta is 45 degrees. We want to plot the point. We want to list 2 other pairs of polar coordinates as well, and give the rectangular coordinates for that point. So there's quite a bit going on here for this one. So to get started, let's get started with that graph. Now when we're talking about the graphs, the 45 degrees, I'm going to run up here, and I'm going to grab this one. I kind of like this one more. The other one that has all of the different circles and angles on it can get a little busy. Okay. So the first thing we're going to do is graph. So I go out 45 degrees. So this is called my pole. The x-axis is the pole, and I go out 45 degrees. From there, bisects quadrant 1, and I go out with a radius of 3. So 1, 2, 3, and there's my point. So that is the point that I'm looking at, and I'll call it P. So A is plot the point. We did that. Part B says give 2 other pairs of polar coordinates that would work for this. So I want to give one that has a positive radius and one that has a negative radius, for instance. So let's go ahead and look at some point P. I could go 360 degrees around and then another 45 to get back to this point. So that would be the point R is 3 and theta is 405 degrees. So that's an example of another point to describe the 345 degrees. I want to do one where we have the negative 3 as well. So if we think about the negative 3, it would have to reflect down into quadrant 3, and I'd basically have to plot this point and then make the R value negative. So for this point, I could do a negative 3 pi over 4, for instance. Negative 3, and I guess we could look at one more. This would be 5 pi over 4, and that would get us back to that same point P. So lots of different examples there. Last, it says give the rectangular coordinates for the point. Okay, so what I want to do here for the rectangular coordinates is I kind of want to draw a triangle in that first quadrant. So if we look at that first quadrant, I know I bisected it. So here's my 45-degree angle. The radius was 3, and basically I need to figure out what x and y are for this situation. Well, there's a couple different things that we could do here. I know this is a 90-degree angle because I dropped that as an altitude down to the x-axis. I know then this has to be a 45-degree angle as well. What I know about a 45, 45, 90 triangle is that I have two equal angles, and I have two equal angles, I have two equal sides. So that means x and y are going to be the same for this particular case. So here, x squared plus y squared would equal 3 squared. But for a 45, 45, 90 triangle, x equals y. Because I have two equal angles, the sides opposite have to be the two equal sides as well. So I could look at this and let's say call them both x. X squared plus x squared equals 3 squared. 2x squared equals 3 squared. X squared equals 9. I'm going to go ahead, 3 squared is 9 halves. And then from here, what I can do is take the square root of both sides. So here I'd have plus or minus root 9 over root 2. Now I'm in the first quadrant, so I'm just going to use the positive here. So this would be 3 root 2. And I'm going to multiply top and bottom by root 2, so this would be 3 root 2 over 2. So my x coordinate would be 3 root 2 over 2, and that would be the same as my y coordinate. Now let's think about what we already know for a 45-degree angle. So from the unit circle, we know the sine and cosine for a 45-degree angle is the square root of 2 over 2. But notice that since my radius has changed to a 3 instead of a 1, it looks like I just have multiplied the 3 by the square root of 2 over 2 that I'm used to having anyway. So that kind of made that problem a little bit easier when we can see the connection between that and the unit circle. Let's go ahead and look at another similar problem. I want to make sure that we get used to quite a few different ones, so that way when you come across the harder ones, you're ready for those. So for this one, we are looking at -4, 135. So I'm going to go up and grab this again. And so we're asked to graph, give two other points, and give the rectangular coordinates. So we have kind of the same thing going on here. So what I'll do first is I'll go over here to do the 135. So let's look at that 135. 135 bisects quadrant 2, and this says to go out 4 units, 2, 3, 4, but I'm not going to put a filled point. This is just kind of my point that shows 4 135 degrees, but I need a negative here. So what it does is it reflects directly across into quadrant 4. Let me make that more of a 45 there. I don't know if that was an improvement or not, to this point right here. So this is the point -4 135 degrees. Okay, so these work out pretty slick, pretty simple, straightforward to graph. So that's part A. Now part B, they would like us to find some other points as well that work with this. I'm going to go ahead and call this point P. So again, -4, 135. So I'm trying to find other points to describe this. Well, I think one of the easiest ones I can see is a +4, -45, because that puts me right to this point right away. Another one I can see is if we come clear around, this would be 315 degrees. Now I want to include one with a negative radius as well. So if I want to think about the negative radius, I'm going to have to think about how else could I get to this point. Well, this would be a -180. Another 45 degrees would be a -225. So that would be another way we could describe that point. Now the next thing I want to do is convert to polar. So I'm going to be, convert to rectangular. We already given polar. So I have this point down in the 4th quadrant. So I'm going to look down in that fourth quadrant. This is 45 degrees. That's the reference angle here. And then when I have a look at this and this is a 4, I can start already thinking about, oh, this is 45 degrees. This is an X, this is a Y. I know when I convert this to polar or to rectangular, I'm going to have a positive X and a negative Y because I'm in quadrant 4. So right away, I kind of think that I know my coordinates from the last problem we did. Last problem we did, we just had the square root of 2 over 2 because I knew that that was the sine and cosine of a 45-degree angle. But then I multiplied that by 4 with my radius. But since I'm not positive about that, let's go ahead and look at actually working through this problem. We're going to use that same idea. X squared plus y squared equals 4 squared. And then keep in mind for a 45, 45, 90 triangle, x and y are equal. So this would be x squared plus x squared equals 16. 2x squared equals 16. X squared is equal to 8. X is equal to plus or minus the square root of 8. The square root of 8 has a factor of 4 for a perfect square. So here I get x equal plus or minus 2 root 2. And that would mean y equal plus or minus 2 root 2. Now for our situation, I know x is positive. So x is going to be positive and y is going to be negative because I'm in quadrant 4. So x is 2 root 2 and y is negative 2 root 2. And again, I'm in quadrant 4, so y is negative, x is positive. And you might say, well, wait a minute, what happened here? I thought we'd have square root of 2 over 2 times that radius, and we actually do. So if we took 4 times the square root of 2 over 2, the 2's would cancel and I'd be left with 2 root 2. So it works just like we actually expected. It just looks a little bit different when it's been simplified. We don't see that root 2 over 2 factor that we might expect to see. So you're going to work through quite a few problems like this. Some of them will be in degrees, some of them will be in radians. The process is the same. If you want to convert everything, you can. Just if you're better working with one than the other, that's absolutely fine. Just make sure when you input your answers that you've converted back to the form that they've requested. Now usually we are given polar and asked to work a problem. For this next one, we are going to be given rectangular and asked to work backward into polar. Okay, let's have a look at that. So here we have the rectangular coordinates, 5 root 2 over 2, 5 root 2 over 2. We want to plot the point, give 2 pairs of polar coordinates, and with the 2 pairs of polar coordinates, they're saying theta has to always be between 0 and 360. Well, a couple things I note right now. I know 45 degrees is involved because this is my square root of 2 over 2. And I think that the radius is going to equal to 5 because I see this 5 right here. But that's what I think. So that's what I think is going on. But we'll see. We'll figure out when we get to that point. What I don't know is which quadrant are we in. Okay, so because I don't know which quadrant we're in quite yet, it looks like it's going to be quadrant 1. I can't really make all of these for sure predictions, but I'm pretty sure that's what we're going to see here. Okay, so let's go ahead and first of all plot the point. I'm just going to use the rectangular coordinate system. So I'm going to go over 5 root 2 over 2, and I'm going to go up 5 root 2 over 2, and that's this point right here. And let's go ahead and sketch everything else in. Here's my triangle. Now in the polar coordinate system, that would be this circle, and there would be circle with radius 4, 3, 2, and 1. Okay, so that's how this would kind of relate to that. A couple of things that I want to keep in mind. This I'm definitely in quadrant 1, so I think to convert to polar, remember polar is r theta, my radius is definitely going to stay at a 5, and I'll show you how we know that, not just from my initial look at this, but I'll show you how you can figure that out. And theta is 45 degrees because x and y, this x value and this y value, are the same. And so if I have two equal sides, that means I have two equal angles. So I know I have a 45 and a 45 here. But if we didn't know that, how would we figure that out? Well, we'll go into that here in just a second. We need to find one other point. Theta has to be positive. So it has to be reflected from somewhere over here in quadrant 3. So if I could figure out a way to describe this point, negate the r, this would reflect across to this point right here. So I think that we're going to have a negative radius, and in the fourth quadrant, the angle that's a multiple of 45 would be 225 degrees. So these are my two values here. Now, how could I figure this out if I didn't see that connection? Well, let's go ahead and just kind of blow up this triangle right here and kind of ignore everything else for now. So we know that this is a 90-degree angle. We know this is 5 root 2 over 2. We know this is 5 root 2 over 2. That's all we know. We don't know r technically. We don't know these angles. Okay, so let's kind of clear our mind and think, oh, we don't know what that is. Well, what we have here for theta then, we have tangent theta is opposite over adjacent, or y over x, however you want to think about that. So tangent theta here is 5 root 2 over 2 divided by 5 root 2 over 2, which is 1. So tangent theta is 1. Well, what angle has a tangent of 1? 45 degrees does. Or you can use the inverse tangent on your calculator as well to figure that out. So theta would equal 45 degrees here. So I know this is 45 degrees. And now what I need to do, I just figured this one out, I need to figure out what r is. Well, the easiest way to figure out r, remember, r squared is equal to x squared plus y squared. So r is the square root of x squared plus y squared. So 5 root 2 over 2 quantity squared, 5 root 2 over 2 quantity squared, square rooted. So I have 25 times 2 over 4 plus 25 times 2 over 4. So 25 times 2 is 50. I guess the 2 would cancel into the 4. So this would be 25 halves plus 25 halves square rooted. This would be 50 over 2 square root of 25, which is 5. So I get r equal 5 here. So that's another way I could have come up with r equal 5. And that's the way you're probably going to have to use it normally. Okay, but for this particular example, it turned out pretty slick that we could recognize that the 45-degree angle was involved. So for our next one, we are given that we have a rectangular equation, x squared plus y squared equals 25, and we want to give the equivalent polar equation and sketch its graph. So first of all, if I wanted to sketch this graph on my calculator, I would have to solve for y, and then I'd have to look at the positive and the negative roots. So there's going to be quite a bit to this one. And also on this one, I want to start looking at graphing in the polar system. So to get started, we need to recall a couple of things. First of all, x equal r cosine theta and y equal r sine theta. And when we have a polar form means r equals stuff. So for x, I'll have r cosine theta squared plus r sine theta squared equals 25. So this would be r squared cosine squared theta plus r squared sine squared theta equals 25. I could factor out an r squared and I'll be left with cosine squared theta plus sine squared theta, and hopefully that's familiar to you because that's one of our Pythagorean identities. This is equal to 1. So I have r squared times 1 is r squared. So I have basically r squared is 25. I go ahead and take the square root of each side and I have r equal plus or minus 5. So this is the polar form. So if you wrote this out, this would be r equal negative 5, r equal 5. So this is the polar form. Now we want to graph this. So let's go ahead and pull our calculator in. For our calculator right now, if we look up here, it doesn't clue me in that we are in polar mode. We would get that clue when we clicked on y equal. Apparently it's still spinning here. I might have to shut this down and go back in. So give me a second to get that reset. Okay, so I got this reset, so hopefully this will work good. So we're in radian mode, and if we hit y equal, we can see we're in rectangular mode because I see a y equal. So if I were to graph this, let's see if I can scoot this over a little bit. If I were to graph this in rectangular mode, I'd have a little bit of trouble. So this is x squared plus y squared equals 25. I have to solve for y, so I would get y squared equals 25 minus x squared. We take the square root of both sides, and I'd have a plus or minus out front. So if I wanted to graph this, I'd have to graph, first of all, the positive portion of this, 25 minus x squared. And if we hit the graph on here, we might have to adjust our window. I get the top part of the circle, and it doesn't look really circular. Yeah, the scales are correct. It just is a distortion of the picture. So it kind of almost looks more like an oval here. Now to finish this off down here, then I would have to come down and do the negative square root of 25 minus x squared. And that would be the bottom part. If you want to make this look more circular, we'd have to change our scale, but this is a circle. Now the polar coordinate will do this all at once. So to get to the polar mode, we go to mode. We come down here where it says function, and we come across to polar. So under the polar graph, notice those have disappeared. I need to graph r equal 5 and negative 5. Let's just do negative 5 first. Oh, it's the whole thing. And then y equal 5, and that would be the same picture. Run one right over the top of the other. So again, it is a circle. Radius is constant at 5. The negative 5 would mean the reflection of that. So that's the graph. That's what this looks like. So getting used to graphing these is very, very helpful. I'm not very good at thinking about things in polar form, so being able to have a calculator to help me graph those is really helpful. Rectangular form, I can usually visualize what's going on, but polar form's a lot tougher. And we can maybe look this more circular if we squish it up a bit. Yeah, that looks better. Looks much more circular. Okay, so that's the graph as well. So a couple things to keep in mind. Always use your calculator to double check and graph anything that you can, because it will make things a lot easier for you. Now along the lines of graphing, I'm going to pull in a screenshot. This is from your e-text. So if you haven't looked at your e-text, it's pretty helpful, something to keep in mind. And the e-text has this nice summary table that I want to show you of different types of polar graphs. Okay, so let's get this squished down to a reasonable size. And these are some different types of polar graphs. So polar graphs are not like the graphs that we usually see for our linear graphs. I'm going to make this a little bit bigger so it's easier to see. These are different shapes that you probably haven't seen before. These always remind me of a spirograph, an old kid's toy, a spirograph. So we have a couple things here. We have circles. So if we have anything that's of the form r equal a cosine theta or r equal a sine theta, it's going to create a circle. Okay, and the circle we just looked at was x squared plus y squared equal r squared, or just r equal 1. So we have circles here. We also have this other shape that almost looks like a sideways infinity sign. This is if r is squared and a squared and the sine of 2 theta. We also have these shapes down here. These are also called cardioids. So I'd like to include that here, because in your homework you're going to run across some that ask you about cardioids. Okay, so that cardioid has that kind of little belly button depression here. And these loop up are not cardioids, or at least are cardioids of a different way. And what we can do when we have these particular shapes, what we can do is compare the A and the B, and then we can kind of get an idea of what that shape will look like. We also have these nice rose curves. So for these rose curves, you can see that if n is 2 or 4, so basically if n is even, we end up with an even number of these petals. If n is odd, then we end up with an odd number of leaves. So these are really some cool shapes. Your calculator will graph all of these, and I'll show you how to do that while we're checking through here. So along those lines, let's go ahead and look at another problem from my math lab, since we have these different shapes that we can kind of refer to now. Okay, so let's go ahead and pull this one in. Now, if you didn't have a calculator to help you with these, what you would do is just plot a few points to come up with which one is your correct graph. But believe me, it's a lot easier if you can graph these. So give a complete graph of the polar equation r equals 7 plus 7 cosine theta and identify the type of the graph. So r equals 7 plus 7 cosine theta. So I could plot some points here. I could plot, let's say, I'm going to choose different values of theta. So I could choose theta equals 0 degrees. So if theta is 0 degrees, the cosine is 0 is 1. 1 times 7 is 7. 7 plus 7 is 14. So r would be 14 then. That would be an example. Pi over 2. Actually, I better stick with degrees here. Cosine of 90 degrees is 0. 0 times 7 is 0. 0 plus 7 is 7. I could do 180 degrees. Cosine of 180 degrees is negative 1. Negative 1 times 7 is 7. Negative 7 plus 7 is 0. I could do 270. And I'm going to end up with 7 as well, and then back to 360. I should be back to 14. Now this isn't all that helpful in terms of graphing because this is only giving me a few points. So it looks like 14 is the furthest I go out, so I'll mark these as 14. So at 0 degrees, I'm at 14, so I'm here. I'm sorry, I'm here. At 90 degrees, I'm halfway, I'm at 7. At 180, I'm at 0. 270, I'm at 7. And 360, I'm at 14. This does not help me picture what this is. So that's why it's going to be really nice to have this graph to look at to figure out what's going on. So let's go ahead and pop in our calculator. And again, we're graphing 7 plus 7 cosine theta. Actually, before we do that, let's scroll up a bit. 7 plus 7 cosine theta. So which one does this match? That would match this one right here. So r equals 7 plus 7 cosine theta. So it looks like to me it's going to be a cardioid. Here a and b are both 7. 7 over 7 is 1. So I think it's going to be a shape probably just like this one right here. But let's see if that turns out when we pop our calculator in. So we go to y equal, and I have my radius here, so let's clear that out. 7 plus 7 cosine theta. We hit graph, and that definitely matches the one I thought. So let's go ahead and go to window here. I need to go further out in the x direction to x max. We could maybe go out to 20. Yep, now we can see the whole shape. So that's our graph, and it matches the one that we thought it would from that chart. So that worked out pretty good. Now how does it relate to the points I just plotted? Well, the points I just plotted are on here. So here's the point 1, 2, 3, 4, 5, 6. So there's the 7. There's the 0. There's the negative 7. And here's the 14. But what it doesn't tell me is what's going on in between. So plotting your quadrantial angles is helpful, but you'd have to plot a lot of points to figure out exactly what's going on with this. So again, this is a cardioid. And coming up here to look at this summary table of graphs, it fits this one right here because r is equal to a plus b cosine theta for the one that we just did. We did 7 plus 7 cosine theta. So a and b are both 7. 7 over 7 is 1. So that gave us this shape right here. So that would be a good way to evaluate these. Okay, let's look at another one for graphing. Okay, so for this one, we want to do the same thing. We want to graph. And then identify what type of graph it is. So we have 7 cosine 2 theta. Well, let's go ahead and go back up to our summary sheet. 7 cosine 2 theta. Well, all of these up here are just single thetas. There's no 2 thetas here. Well, here's one, but I don't have an a squared out front, and I don't have an r squared either. So if I come down here, here's my 2 thetas. So I think it's going to be a rose curve of some sort. Okay, now for the one I'm looking at, we have 7 cosine 2 theta. And so n is even, so I think we're going to have a picture maybe something like this. Now notice the difference between these roses. The vertical, I have a petal on top and bottom. Now over here, when I have a petal, I only have it just the top. I don't have the reflection point here. So these are symmetrical. These odd ones are not. So I think we're going to have a rose that looks like that. Okay, so I think this is definitely a rose curve. And we're going to just graph this on our calculators to figure out what's going on here. So let's go ahead and pull the calculator in. 7 cosine 2 theta, so y equals 7 cosine 2 theta. Let's graph it. So definitely a rose curve. And if you wanted to adjust that to center it, you could, but this is a rose curve. And I can get that from that table of curves as well, but having that real point that we're looking at, that real graph that we're looking at, makes it a lot easier to compare those. So definitely a rose curve. We've already looked at one that was just a circle. That was when it just had a constant radius. That's the type of thing you can graph on your calculator as well. And I'm just double checking through here to make sure that we've seen some of everything, and I believe we have. So when you're working through these, make sure you keep track of that. Oh wait, this is one we haven't seen before. R equal negative 20 cosine theta. Oh, that's okay. That's just going to be a circle. Yeah, we've seen that. So when you're working through these, please make sure that you're keeping track of those first formulas that we started with. So if we scroll up to the top, and we've used these formulas over and over again throughout the class, but if you don't have them on a note card, make sure you get them on a note card. Okay, so these that are down here in the red. As usual, if you have questions, please let me know. You can send a screenshot of your question and your work, and it's really easy for me to help you out. So good luck on this assignment, and please let me know how I can help.